Good afternoon, everyone. This is just to give you a recording notice. This lecture is being recorded. If you have any concern, you need to contact me, please. What we were doing in the last lecture, we were trying to learn about the marginal probability distribution. That's what we were doing in the last lecture. We have done for discrete random variable. Now today we are going to start the marginal probability distribution for continuous random variable. Now for this random variable, the formula for the marginal distribution is f of x at x is equals to f of x of y, which is the joint probability distribution, and we take its integral from minus infinity to plus infinity. And in case of y, we have f of y the same, the joint probability distribution, f of x of y in terms of x and y, and we take its integral from minus infinity to plus infinity. Now this, I did not write it down intentionally, the derivative here, because I just want to highlight. If you have x variable here, this equation needs to be integrated with respect to y. And if you have y here, this equation needs to be integrated with respect to x. So that's why my d of x comes here. This is one of the most important point in marginal probability distribution. I will be going back to change my color. Folks, I need to go in the next slide, please. Now this is the example that we were doing before, and we will just expand it. This example statement comes from lecture 10, I believe. So this is just the continuation of that example. So a healthy individual this was the statement here. Now in this statement, it is asking us to find the marginal distribution of x and the marginal distribution of y. And the third objective is find the probability that healthy individual has a sugar level, it should be sugar level between 150 and 200. So the purpose of taking this question is to show you how do we find the marginal distribution for continuous random variable. Now, if you recall from this example, our x was ranging between 8.5 and 10.5, whereas our y was ranging between 120 and 240. Folks, I need to go to the next slide, please. I'm going to do the part 1 on the next slide, and then we will go one by one. Now, in the first part, I need to find out the marginal probability of x. Now, for that one, we know f of x is the joint probability distribution of x and y, and then we integrate. Because we have x here, this integral should be with respect to y, and the y limits are from 120 to 240. Now this thing we find out in the previous question, like in lecture number 10, it was 1 over 240, and we just integrated from 120 to 240 times d of y. So once you solve it, you will get 1 by 2. Now in the part B, or the second part, it was asking to find out marginal probability of y. For that one, I know this is my f of y. That should be the joint probability of x and y, and it should be integrated because I'm interested for y. This should be integrated for x, and the x limits are from 8.5 to 10.5. Now this one, again, the same thing. We know it is 1 over 240, and we integrate it from 8.5 to 10.5 times d of x. Once you solve this, you will get 1 over 120. So that's your answer for first part. That's your answer for the second part. Folks, I need to go to the next slide, please. In the third part, he was asking to find out the probability when your sugar level was noted as the y, is between 150 and 200. That's what we need to find out. Now there are two ways that we can solve this question. The first is method 1. The first is we use the joint probability distribution. Now in that case, our probability should be, so the X range remains the same, which was between 8.5 and 10.5. However, our Y range is the new range. The Y is between 150 and 200. Now we apply our formula here for the joint probability distribution, which was f of x of y for x and y, and we integrate it 2 times, d of y and d of x. Now the y limits we know, this inner integral is for y, so this can be from 50 to 200, which is my limit of the y here. For x, the outer integral is for x, my limit is between 8.5 and 10.5. So this one should be 8.5 and 10.5. Now just a small point here, if you change your derivative, just make sure you also change your integral as well. By that I mean to say, if you want to bring this x here, your integral limit should also be coming here. Now this f of x of y, which is joint distribution, it was 1 over 240, and it should be integrated between 150 to 200 and 8.5 to 10.5, and this is your dy times d of x. Once you solve this, you will get over 12 as your answer. Now this is the method 1 that we are using our joint probability distribution formula. The second method could be, we can use the marginal probability distribution. Okay, I need to go to the next slide, please. So what could be your second method? Method number 2. It's the marginal probability distribution. So the y should be between 150 . This is for f of y into d of y. This is the PDF of your y, and it should be integrated between 150 to 200. Now this is so 1 over 20. Now once you solve this, you get the same answer as 5 over. Now this one, 1 over 20, we did it in lecture number 10. Folks, I go to the next slide, please. These numerical were the part of the last lecture, but we could not finish it. Now our today's topic is the conditional probability distribution. Now this formula you have seen in your statistics courses, probability of A, given that, this is a symbol for the given that B is equals to probability of A intersection of B over probability of B. Now what we are going to do, we are going to study the conditional probability distribution for joint functions. Now in that case, the similar formula can be expanded. Probability of X is equals to X, given that I'm taking X and Y as a variables here. Y is equals to your Y is equals to, on similar basis, the joint probability distribution, which is noted as P of X divided by, because talking about joint probability distribution, this distribution will be your marginal distribution of Y. So this will be P of Y. So this one is my probability distribution, whereas this one is my marginal distribution of Y. Marginal distribution. Now this thing is also denoted as P of, now you need to pay attention here because I'm talking about the conditional probability here for joint. So P of X, it is the conditional, given that now this Y should be come in the lowercase and X given that Y is equals to, this joint probability distribution can also be denoted as P of X of Y of X and Y divided by your marginal distribution of Y, so which is the P of Y. Now this is what we call as the conditional probability mass function, because we are talking about the discrete random variable. I should have mentioned it here earlier. So we are talking about the discrete random. So this conditional probability is the conditional probability mass function. This is also written as P of X of Y for X only. I will explain you these one in more details when we go next. Folks, I need to go to the next slide, please. Now, just like we were studying the mean, just leave some space here. And we were also studying, leave some space here, the variance. In case of the conditional probability distribution, this mean is called conditional mean. Conditional mean. And this variance in case of the conditional probability distribution is called as the conditional variance. Conditional variance. Now I will start from this one, conditional mean. The expected value of y given that, now as I said, it should be the lowercase now, is equals to expected value of your y given that x is equals to x, or I can also write it down as the mu for the mean. Now because it is a conditional and I'm interested for y given x, so this mean should have a subscript of y given x. And how do we find it? We take our conditional probability mass function. Now in this I need to have it in terms of y given x. In the previous slide we have x given by y. I will also write down that formula. We are interested for y here, and you multiply it with your y and take the summation. This one should be for all x. Now in case you are interested for expected value of x given that y, this can be represented as mu of, I'm interested for x given that y, so subscript should be x given that y is equals to, because I'm talking about x variable first, so the x should be multiplied by the conditional probability mass function, and this subscript should be the same, x given that y. Of x, and then I sum up for all y. Now this is the definition, these are the definitions for your conditional mean. In the next slide, I'm going to define the definitions for the conditional variance. Folks, I need to go to the next slide, please. Now for conditional variance, just keep in mind we are doing for discrete random variable so far. Now the variance is represented as var, VAR. Again, we are talking about the conditional, so it should be, let's say I take first for y given that your x is the lowercase here. That should be the same formula, but in terms of the conditional probability. Y minus mu. Again, this mu, it should be in terms of conditional, so I will write it down y given x whole square. We sum up this all x, and then you multiply it with probability. Or we can also find out this conditional variance using our formula of y square is multiplied by the probability of y given x I sum up them all x, and we subtract mu value, mu square value. And because we are interested for y by x, so it should be y given that x. I mean, it should not read as a y by x, it is at x. Now, in terms of conditional variance for x given that y, the same approach as we are, it should be x minus mu, and because mu should be based on x given y, and we take the whole square, sum them up for all y, multiplied by your conditional probability here of x, or I can write it down as x square times the probability, conditional probability here, this is your capital of x, and sum up for all y, and we subtract our mu square. And because we are talking about x given that y, so this one should be the same, x given that y. Folks, I need to go to the next slide, please. Now those were for discrete random variable. In case of continuous random variable, in case of continuous random variable, we have of x of y. Again, it should be the lowercase as given that of x is equals to your joint probability distribution f of x of y, and it should be divided by the marginal probability. Because we are talking about x here, this one will be for y. In terms of f of y given that x, or y variable, this is equals to the joint probability distribution and it should be divided by your f of x, because I need it for f of y. Now these two, in terms of continuous random variable, these are called as the conditional probability density function. That's because we are talking about the continuous random variables. These are called conditional probability density function. Folks, I need to go to the next slide, please. Now, similarly, continuous random variable, I will define the conditional mean and the conditional variance. Now, the expected value y given that x will be, now the only difference is we integrate it here. I have my conditional probability density function f of y given that x of y into d of y. We integrate it from minus infinity to plus infinity. The second case could be for x given that y, that is equals to, well, I missed a y here, it should be, because that's for the mean here. This one should be x times the conditional probability density function f of x given y and then we integrated from minus infinity to plus infinity. Now the conditional variance of y over x. Now if you recall, the variances can be noted as x sigma square. Because I'm talking about conditional, so it should be y given that x, that is equals to, we take our y square value, because I'm interested to find out for y given that x, and multiply it with the probability density function, conditional probability density function of f of y given x into dy, and then we integrate it from minus infinity to plus infinity, and we subtract mean value, square of the mean value, because we are interested for y given that x, so this mean should be for y given that x. Now on a similar note, we have the conditional variance for x given that y. This is equals to your sigma of x given that y. This is sigma square. Now because I'm interested for x, it should start with the x here, x square times the conditional probability density function in terms of x given that y, and we integrate it from minus infinity to plus infinity, and then we subtract our mean, conditional mean value, the square of your conditional mean value. Because we need it for x given that y, this conditional mean should be x given that y. Folks, I need to go to the next slide, please. Now, if your x and y are independent, or marginal conditional probability for discrete random variable p of x given y will become p of x. This is what I mentioned in my previous slide. So x and y should be independent, and this is the marginal probability. Marginal probability. In terms of y given that x, we have p of y, and this is again your marginal probability. Now these are for your discrete random variable. Now if x and y are independent in a continuous random variable, you have f of x given that y, that should be equals to your marginal probability of. If you have y given that x and x and y are independent, this should be equals to your marginal probability of y. Now these are the relationships when you have the continuous random variable. Folks, I need to go to the next slide, please. Now in the next slide, I will have an example for you, so it will make more sense how these formula works. Now we are going to do one example here. The joint density function of two random variables x and y can be represented as this is the joint density function f of x of y for x and y is equals to c. C is a constant here, x square minus times y square minus 9. When you have the limit of x greater than less than 0 and 2, and your y limit is greater than equals to less than equals to 3, or it will be 0 elsewhere. So by that means if your value is out of these two limits, this will be 0. Your joint density function will be 0. Now our objectives are, first we need to find out what is the c here. What is the value of the c? C is a constant. And the second objective is we need to determine marginal density function for x. Third is you need to determine marginal density function for y. The fourth objective is, are X and Y independent? The last objective is, we need to find the probabilities when X is greater than 1, given that, now this is 1 here, given that your Y value is 2 and we need to find the f of X at the value of 1 and 3. These are our 5 objectives for this example. Folks, I need to go to the next slide, please. Sorry, this one is, yes, this is the capital here. Objective is, we need to find out the value of your constant, value of constant C. Now for this one, we are going to use the two conditions of joint density function. Now f of X of Y to be a joint distribution function, there are two conditions. The first is, your joint probability distribution should be greater than equals to 0. And the second important property is, the sum of the integrals of your joint probability distribution should be equals to 1, because this will give you the sum of your all probabilities. And we are integrating it from minus infinity to plus infinity, minus infinity to plus infinity. Now this function he already mentioned into our statement. This is the C times x square minus 4 times y square minus 9, and we need to integrate it with respect to y and x. Because my inner integral is with respect to y, the limits of the y should come here, which are ranging from 0 to 3, and the x limit is outer, so the limit should come here for x, which is from 0 to 2. This should be equals to 1. Again, it does not matter if you put x first and the y after, just make sure you also flip your integral here. Now I'm going to give you some help here how we proceeded. I'm sure you know about this. So c into x square minus 4. This limit is for the y. So I'm going to integrate this function with respect to y. It will be y cube over 3 minus 9 integral of 9 will be 9 of y. And for these ones, we have the limit from 0 to 3. Your d of x is equals to 1.0. It will be c of x square minus 4 times, now I apply my limit, upper limits minus the lower limit. So the upper limit is 3 cube over 3 minus 9 times 3. Now the lower limit is 0. So this will become 0, this will become 0. 0 minus 0 will become 0 of d of x, and the integral will be from 0 to 2. That should be equals to your 1. Okay, so I need to go to the next slide, please. Now in the next slide, I'm going to simplify this one and see what number I get. Now once I simplify that, I have c of here minus 4 times minus 18 is the number that I get, times d of x, and integral from 0 to 2, that should be equals to your 1. Now if you look on this integral, c is a constant, minus 18 is also the constant. I can take them out of the integral, so it will be minus 18 of c, integral from 0 to 2 of minus 4 into d of x, that should be equal to 1. So it will be minus 18 of c. Now I integrate my x here, it will give you x cube over 3 and minus 4 of x. These should be the limits of 0 to 2. It will be minus 18 times of c. Now the upper limit 2, this will be 2 cube over 3 minus 4 times of 2, and minus the low limit is 0. So this will become 0 minus 0, which is 0, is equals to 1. Now you don't have any variable here, the only thing is the c. So once you find your c, that will be 1 over 96. And that's what we are interested to find out. Folks, I need to go to the next slide, please. Now in part 2, he was asking to find the marginal probability of x, which is f of x. The same formula, we have the joint probability here for x and y. Now, as I said, because we are interested for x, this should be integrated with respect to y. Keep this in mind. And y integral is from 0 to 3. Now we just find out our constant in joint probability distribution. We plug that constant, we get 1 over 96, x square minus 4, y square minus 9. Once you solve it, you will get minus 3 over 16 of x square minus 4. I just want to give you a refresher here for integration as if you have x that you need to integrate respect to y, this x is constant. This will come out of your integral because we are integrating respect to y. So this one should be x of integral of your y, dy. And the integral and d cancel each other, you get x times y. And the same is the case if you have, we will have that in the next part 3 actually. If you are integrating y with respect to x, this y is the constant. It can come out of your integral. So it will be y times integral of d of x. And integral and d cancel out each other because they are anti, so we get y of x. Just keep this in your mind. Now this is to apply in the part 3, where he was asking to find out the marginal probability of y. So it is f of y. I have the joint probability f of x of y. Now because I'm interested for y, I use my x derivative, x integral here. And the limits of your x are from 0 to 2. Now this is your joint probability distribution. Is given to you 1 over 96 x square minus 4 into y square minus 9. We integrated for x from 0 to 2. Now once you solve it, you will get minus 1 over 18 of y square minus 9. Now before I go, that's your answer here. Before I go on the next slide, just notice a small point here. We were interested for finding the x. So your final answer of the marginal distribution of x should have x in it. This is what the confirm. This confirms your calculations. If you are not getting x, so there is something wrong in your integration. The same is true for y. I'm interested to find out a y function. So your final answer has the y in it. Folks, I need to go to the next slide, please. Now, in the fourth part, he was asking if x and y are independent. As I mentioned earlier, if x and y are independent, then your joint probability distribution should be the product of your individual probabilities. Now, this is what we are going to check now. This is your marginal probability of x, which we just find out in your part 2, which is minus 3 over 16 times x square minus 4 minus 3 over 16 times x square minus 4 times the marginal probability of y. Again, in your part 3, we just find out our marginal probability of y. It should be multiplied by minus 1 over 18 times y square minus 9. To solve this, you will get 1 over 96 of x square minus 4 times y square minus 9. Now, this what is equals to the joint probability distribution in your question statement. Now, hence we can say that x and y are independent. Now here I just want to share something with you. If this is not equal to your joint probability distribution, y and x and y will not be independent, they will be dependent. There is a technique that we use, it's called cupola. This is an advanced level technique we use. We use it x and y are dependent. That's not the part of your curriculum, but just for your information. When x and y are dependent. This is what you study most of the time in your PhDs. This is not the part of your curriculum again. Folks, I need to go on the next slide, please. Now, in last part, number 5, he was asking us to find out your probability when x is greater than 1. This is 1. Given that your y is equals to 2. That's what we need to find out. Now, as you can see, this is the conditional probability he's asking us. So first we need to find out our conditional probability density function. And for that one, we have f of x of y. That is equals to your joint probability distribution. If here is x, this one should be y. Now this one we know from our question statement, which is 1 over 96 times x square minus 4 times y square minus 9. And this is the marginal probability of y. We just find out in part 3, I believe. So this one is the minus 1 over 18 of y square minus 9. Now this thing will be cancelled out from this thing because they're same. So the leftover is the minus 3 over 16. Once you solve this, x square minus 4. Now we have the conditional probability density function. Just for your information here again, this one is equals to your f of x. So this also confirms that x and y are independent. Folks, next slide, please. Now I'm interested to find out p of x greater than 1 given that y is equals. Now because x and y are independent, I will be finding out p of x where x is greater than 1. I have for this have the marginal probability of X from 2 for the limit of X. So it is minus 3 over 16 X square minus 4 times d of X. I make a mistake here which I want to correct it. It is good I made it. I'm interested for this value. If you look on the X limit, it was from 0 to 2. He's asking me for X when is greater than 1. So this lower limit should not be 0. It should be 1. So let me correct. Oops, sorry. So it is starting from 1 to 2, not 0 to 2. Because the statement is asking me to find out X when it is greater than 1. So once you solve it, you will get 0.3125. In your part 5, we have f of x of y. We need to find out at the value of 1 and 3. This is same as I say that the probability value when your x is less than equal to 1 and your y is less than equals to 3. Now this one we use the joint probability distribution f of x of y. We integrate with respect to y and x. Now the y limits are from 0 to 3 and the x limit should be from 0 to 1 because here he's asking us the maximum limit is 1, not 2. Folks, I need to go to the next slide, please. Now in the next slide, I'm just going to plug in my disjoint probability function here. This will be equals to 1 over 96 x minus 4 y square minus 9 dy of d of x, and we integrate it from 0 to 3 and 0 to. So once you solve it, you will get 0.6875. That's your answer. Now folks, everything we have studied so far for the joint probability distribution, this is from chapter 5 of your textbook, which is available on D2L, Douglas and George. You can read all the chapters, but I want you to work on these examples. Example 5. This all chapter is very interesting. If you want to study, you are welcome to do so, but at least you need to work on these examples. Example 5.4 to 5. These are on page 145. For your practice further, we have tried to attempt example 15 to 21. These are on page 158. And examples, these are also the examples. Try to attempt examples 27 to 31. These are at 172. As I always say, when you're doing the examples, just don't look at the solution. Go through the lecture and look at the statement, try to solve it on your own. And if you get any problem, then look at the solution. Folks, I will stop it here and we'll take your questions. If you have any, please let me know. Do you have any questions for me, folks? Now on Monday, we have from Hadis, the equation of the conditional variance for CRV, the integral is just for the first term. I'm not sure which slide you are talking about. Okay, let me have a look here. Yes, the integral is only for the first term, Hadis. I can take you back to the slides even. Let's see. Somehow my system is hanged up now. So to answer your question, yes, those are only for the first term. Yes. You are welcome. And the last equation before the example, yes, that's only for the first integral. Yes. Okay, so Yakubu is saying I need to digest the lecture first, sir. Okay, if you digest this and you have any questions, you are more than welcome to email me. Folks, go through the examples that I mentioned. Those will help you to understand more about this. In our next lecture on Tuesday, I will bring one more example. And the next Thursday, we will start our data analysis. I hope every one of you received my invitation for Monday meeting. Just as a reminder, this is a very informal meeting. I will like to take a feedback from you on the course. And we also want to see each other, of course. Folks, is there any more question for me, please? Right. So I wish you a very good weekend, guys. And if you go through this lecture, and if there is any question, please drop an email. I can also to set up a meeting with you if you think something needs to have a discussion on. Thank you and have a good weekend, guys. I will see you on Monday now.